Thank you for coming and for everyone online. So yes, I am an NPMP here in NASA Ames in the Exobiology Branch. And today I'm going to essentially walk you through parts of the initiative that I've been managing, but most of it's actually going to be a bit of a crash course in machine learning, and then a little bit about foundation models at that. So as I said, the initiative is to improve the usage and understanding of AI/ML within the astrobiology community. The way we're doing this is mainly through three ways. We have a community portal that you can access with a QR code there, where there's everything literature reviews to it's curated literature to AI/ML guides. We have a monthly seminar series where there's virtual talks from people all throughout the community. It's not just astrobiology, and those are accessible at the our main portal and on our YouTube page. And then we're also networking with headquarters and the RCNs, the Research Coordination Networks within astrobiology, for things, everything from funding to their strategies. And we even held a workshop in February on foundation models for astrobiology, which if I have time, I'll talk about at the end. But let's get right into it. So AI. So AI is simply computers performing tasks associated with human intelligence. And this is anything from learning to decision making. But really, AI is actually an umbrella term for all of these other aspects that fall within AI. So we do say AI/ML, and I use it interchangeably all the time. But if we're being very technical about it, ML or machine learning is actually a subset of artificial intelligence. And so we're mainly going to be talking about machine learning today. And with machine learning, that's where computers or machines, they're just learning from previous experiences and exposures, really from their data, to improve performance and accuracy. Why would we apply this to astrobiology, though? Well, with such an interdisciplinary field, with it being both complex because of that interdisciplinary and because of the multimodal data that we all collect, that provides us with these very large data sets that essentially can get so big, especially if you start thinking about mass spec, that it can come to a point where it would just be far too inefficient for humans to work with it on its own. And so this is where machine learning can come in and help fill that gap. So this is a machine learning lifecycle. I'm not going to go through all of this. I'm mostly going to hit on elements highlighted here in red, which are part of the exploratory data analysis. This is like the visual analysis of the data, model training, and then a little bit of evaluation. So with machine learning, we'll start with unsupervised learning. So unsupervised learning is simply using algorithms to analyze and cluster unlabeled data sets. So that's the big part here, that the data sets you're working with are unlabeled. And because they're unlabeled, you can't actually look for regular predictions like numerical predictions. You really would be looking for hidden patterns or groupings within the data. And the main ways you can do that are with dimensionality reduction and clustering. So dimensionality reduction is, just as the name implies, you're reducing higher dimensions to low. And when so of course you may think, okay, well, there's 1D, 2D, 3D, 4D. But when you're taking these data sets that are going to be in these massive matrices, you can have thousands of dimensions. You're being well beyond anything that you could visualize with your eyes. And so for many reasons, both for your own ability to analyze the data and to make it more efficient for the machine learning, you can apply dimensional reduction. And you can see this very simplified visual here, where you're taking this 3D cube with color and breaking it down into lower dimensions. Now, one of the main ways we do this is with something called standard principal component analysis, or PCA. This is when you're working with linear data, and that's going to be a key thing throughout this, where you're come across linear and nonlinear data. So really all this is doing orthogonal transformations on the data to look for the principal component, which is really just the part of the data that has the most variance. And you can see that in the image on the left, where the principal component in blue is highlighted, and it has the largest variance. So essentially it has the most spread. And you can also see that occurring in the graph on the right, or the GIF on the right there, where the line is rotating. As it's rotating, if you notice, all of those lines are orthogonal to, or all of the points and the lines connecting to the main line are all orthogonal. And so this is rotating through and determining where the principal component is. And then we'll go from there, you'll get the next principal component, which will be another orthogonal part, which is, again, if you look, it's highlighted there in yellow. So again, this allows you to work with linear data, hence the orthogonal transformation of the linear transformations. It's pretty fast compute, easy to interpret, and it allows you to maintain global structure of your data. Now, I will just highlight very briefly, there is a PCA ability called kernel PCA, where you can work with nonlinear data. So you're actually in there looking through scikit-learn or any early TensorFlow, and you may come across these possibilities. But it's the same as PCA in the sense that you preserve global data structure, but it gives you the ability to mess around with nonlinear. Now, another algorithm that also works well with nonlinear data is the T-distributed stochastic neighbor embedding. It's a mouthful, or just TSNE. And this, again, you're taking higher dimensions and looking at the similarity between the data as you're moving it down. And so really what's happening is you're taking the original multi-dimensional space, you can see there on the left. You have some point of interest, you're determining the distance from that point to the other points, producing a normal distribution of probability from it, and then repeating this in a lower dimension and comparing the differences between those two distributions and minimizing it. And so, as you may imagine, this can be computationally expensive because there's so many points involved that you determine these distances from. It can be a little harder to interpret at times, but the big takeaway is that it provides you with ability to work with nonlinear data. Okay, so now what about clustering? So you remember clustering is where you're now looking at categorizing. So you have and then you can break it down again into linear and nonlinear, and you have k-means clustering or DB scan. So k-mean clustering, this is an iterative process where k is just a value, 1, 2, 3, 4. It's a number you pick. And you're grouping data based on a series of clusters where you essentially have a centroid. So the algorithm is picking a center part within each of the clusters, and the number of centroids is equal to the value of k you enter. This is good with linear data. It's not very computationally expensive, pretty easy to work with. The only drawback is you require spherical clustering because you have that centroid. So spherical clustering, like you can see here, it's fairly grouped. Now, and again, this is a very simplified one. I mean, even just with our eyes, we can kind of see where this grouping is. Now, if you want to work with more ambiguous data that's not very spherical, this is where the density-based spatial clustering of applications with noise, or simply DB scan, comes in. And as the name implies, this is when you're working with density. This is based on the density of the data points within your data. And so a very simple example you can see on the right, where this has already been scanned and color-coded, but essentially the algorithm would go through these different circles, and because of the density along those paths are different and there's space between, it will be able to differentiate them. And because of that, it can also do nonlinear data. It just can be a little tricky because the hyperparameters involved, you need to understand them well to work with this. So now let's look at supervised. So supervised learning is where you're actually involved more in it, because there's labeled data coming in. So with unsupervised, the algorithms don't know what the features are. Here it's actually labeled. So because you have those values, you can actually make predictions. And with this, you have the main ways you work with it are regression and classification. But there's also traditional ML and deep learning can both do regression and classification. One of the big difference, though, is with machine learning or traditional machine learning, there's a feature extraction part where along that pipeline of the machine lifecycle, you have to actually go in and adjust the raw data, essentially apply meaningful characteristics to it. So anything from if you have audio waveform, extracting the frequency spectrum for it, or just applying categories to your different variables. However, with deep learning, because of the number of because of the hidden layer structure of it, and we'll talk about this in a little bit, it does that feature extraction for you. So it's one of the nice things. But how do you actually decide between these two if they could both do regression and classification? Well, it comes down to the data size. So as you can see in this graph, it's showing performance versus data. And so as the amount of your data increases, the capabilities of the different algorithms either plateau or improve. So you can see as you get to, and I would say on the far left, you're just talking about maybe thousands of data sets. So traditional machine learning will work very well with small data sets. But as you increase, you can see it starts to plateau, and deep neural networks or deep learning starts to take over. And this is really because of just the sheer complexity of the deep learning networks. They don't work well with small data sets because it's essentially just it's almost like if you had 30 surveys that you needed to work or analyze, but you gave it out to 5,000 people, like coworkers, to work on it. It would be complete overfitting. It would be a mess. And you don't have enough data to really look at all the different comparisons, where that becomes much easier when you have these very large data sets. Okay, so now back to regression and classification. So regression, this is when you're actually looking at numerical values. So you're looking at understand the relationship between the independent features and the dependent numerical outcomes or values. So this could be anything like the temperature, price of a house. And then classification, that's categories. So maybe do you give a loan to somebody or do you not give a loan to somebody? However, most of the algorithms can do both. And you sometimes even see that when you're bringing up the different toolkits, you can have an option for regression or classification within a specific algorithm. So logistic regression is actually, even though it says regression, it's actually a classification technique. And so this is, like I was saying, this is where you have the categorizing. And it works with the sigmoid function that you can see represented on the right here, where essentially you have 0 or 1. Now, and so that would be like loan or no loan. You can apply a cutoff point though. So if you had something maybe like you could have a cutoff of say 0.5. So if any points were 0.5 or above, then that would fall into the class B. And if it was lower, that would be class A. So that's how you would handle something that was maybe predicted to be in between. And now there's also k nearest neighbor. So this one bases the classification off of the proximity to other data points. So in this graph at the bottom here, if you start on the left, you have your first query point. This is the query points you're trying to classify. And in this example, you have two classes, A and B, and they're color coded. So the k nearest neighbor, the k is again just a number, 1, 2, 3, 4, and it moves out to whatever nearest point is based on the number. So if you say k equals 1, it would move to the first point that's closest and classify based on that point. But if you had really bunched up data, whatever, that might not be the best. And so you have to kind of play around with your k values. And because this is majority based, you actually want to avoid even numbers and just mostly stick with case of that are odds of 1, 3, 5, and so forth. And so in the example on the far right, you see that in this case, this would be for k equals 3. There's 3 points, and it would determine based on just the majority voting that this query point actually applied to class B, or it was a part of class B. But again, there's some iteration here that you would have to go through. Now, another option is random forest. This is actually an ensemble method of decision trees all grouped together. And they're going through, if you follow the GIF here, they're essentially going through, each one of them is a random subset of your whole data. Usually it's not all of it, it's maybe about 2/3. And there's another portion that's left out. And so we'll go through the decision tree, And each one of them, again, is all different. So tree one to tree two won't have the same exact amount of data or the same parts of the data. And it will spit out some prediction. And then because you have all of these together, you do a majority voting. And so in this example, they all said there were two A's and one B. The majority says the answer would be A. And what's kind of nice about this is it does a little bit of internal validation because you have some data that's not part of the validation set. And this is what called the out of bag score. So you still would potentially have to do some validation later on, but it's just nice that with random forest, you actually do get kind of this inherent validation as part of the algorithm. So now let's talk about deep learning just a little bit. So with deep learning, you're teaching a computer to process data in a way inspired by the human brain. And I mean, that is a bit of a simplified idealization of it, but it's still it follows across. If you imagine that you have your dendrites on the left that are receiving the input, your nucleus, which is processing it, and then your axon that is then sending out the information to the next neurons to transmit to. And in a neural network, which deep learning network is made up of, you have the same kind of input output where you give it an input, it has a function and biases, and that middle part is essentially the node or the neuron. It applies these weights and biases and then produces an output or predicts an output. And with deep learning, you would usually need two or more hidden layers for it to be considered deep learning. If you have less than that, then it could just be a regular neural network or considered shallow. And as I'll show in a little bit, for things like the GPTs, those will have dozens of layers. Okay, so now let's look at a little bit with evaluation. So for classification, one of the main tricks you would use is the confusion matrix. And this just compares predicted values against the actual values, and it gives you a visual, which is really helpful. The visual looks like this table here. This is an example. So in this case, it's just binary. You have something that's just positive or negative. And these little green and red boxes represent different things. So for example, FP or false positive, this would belong to the negative class, but that's been classified wrongly as in the positive class. And so all of your true results will be the diagonal of this matrix. And these will actually all be filled in with values. So the true positive will have some number, the false positive will have some number, and then you can evaluate it, whether you determine the accuracy or the precision or the recall. These are some of the main things you can get from a confusion matrix. And you can see this little guy. You can see how you actually solve all these. So the accuracy is just how many correct predictions there are overall. Precision is just the sum of the TP over the sum of the TP plus the false positives. And recall is how good the model is at predicting the positives. And then for regression, you have loss functions. These are just mathematical functions to measure the difference between predicted and actual value. I won't go into all these too much. It's more just to let you know that the coefficient determination R squared, mean square error, and root mean square are the main ones. And then you also can look for mean absolute error and the mean absolute percentage error. But the bigger takeaway is just when you are working with some of these, especially if you are reviewing in a machine learning literature, you see these different equations. And one thing I just want to point out is the y sub I minus y sub I hat is the error. And so when you're maybe reading about these, that would be something you're looking for where somebody is discussing their loss functions. That would be the error. And so potentially be a little easier to find in the literature and just understand what you're looking at. Okay, so let's talk about LLMs a little bit. So large language models are just there to understand natural language. Natural language is just what we're speaking. It's human language, whether it's English, Spanish, Latin, whatever. It's not computer language. That's what the natural refers to. And so it digests text. And it's deep learning based on the transformer model concept, which I'll discuss in a second. Essentially, you just have input text, you process it, and it is outputted. And essentially, that's your prediction that's generated. As I said, it's a neural network with potentially dozens of layers, a massive data set. But the big thing is, or I guess a kind of more subtle thing is, the LLMs don't actually know the answer. They don't actually know that 2 + 2 = 4. This is just a prediction based on their training. And again, so I just highlight some of the main ones. There's Chat, Gemini, and DeepSeek, of course. I don't think we're actually allowed to use DeepSeek on government computers. So if you use that, I guess you can play around with that at home. I haven't actually used it yet. But I have used Chat, and I know that at least here at Ames, I believe we have access to Gemini. At least at STX, you have access to Gemini for free. So you also may have heard LLMs referred to as black boxes, and this is because the GPT, or the generative pre-trained transformer, the first one was 12 layers. The GPT-3 was 96, and 4 is 120. Within those 120 layers, you end up having 1.8 trillion parameters. So those are all those weights and biases. So essentially, these are black boxes because no one can actually tell you when you put something into it, how exactly mechanistically, cause and effect, how it actually moves through all the different nodes and layers to give you the output. We understand the architecture, but you can't actually follow it along because there's just so many sheer different settings and options for the input to follow. And so a great example is, well, the sense when Mary and John went to the store, John gave a drink to who? Well, we would say Mary, obviously. But we don't know why the LLM would pick this. And actually, researchers looked into this for GPT-2, and they could determine that that the LLM was understanding that John should not be the answer. They would understand that John would not be giving a drink to John. And they could follow that back. They could actually follow the node and actually see where it made that decision. But they actually couldn't figure out why the LLM was able to determine Mary. And so that's where this becomes, so these really are a black box. Now, this is research that's ongoing. It may be eventually we will understand that. But at least right now, just because of the sheer complexity of this, it's not something we can understand deterministically yet. Now, what's actually going on? What is the architecture, though? So this is all working with tokens and word vectors. So if you look at the input there, maybe your input is, this is a white tiger. And then the tokenization is just breaking that sense down into words or parts of words. So here, the example is, this is a white tiger. And then you take that and turn each token into a vector. So now you have something, these vectors can be huge. They can be huge and they can be many dimensions. And that may be complex to us, but for the computer, it's easy, especially with matrix multiplication or just matrix processes. And you get these vectors that you can then manipulate. And what's really cool is context can even be vectorized. So say you have the word bank. Okay, well, it could be a financial institution, can also be in a river. We know what it is. How does the computer? Or I always like, so fruit flies like a banana. Was the fruit soaring across the room? Or are we referring to fruit flies, the actual insects? And so the computer or the LLMs can actually vectorize these different, so they'll have a specific vector for bank as a financial institution and a specific vector for bank as a river. And then those come in when we look at the transformers. So transformers, or the concept of transformers, came around from Google in 2017. This was from a seminal paper called Attention is All You Need. They actually came up with it from the Beatles song. But it introduced the concept of the transformer and actually building on this concept of attention, which I'll talk about in a second. But what's really amazing about this is before the transformer, everything when you give an input would be sequential. So it would maybe be John wants his bank to cash. Where with the transformer process, this could now be parallel. So it takes all of that at once. So it's faster. And this is why GPUs started also being used because of that parallel capabilities. So within the LLMs, each layer is a transformer. There's more to it than that. That's a more simplified way to describe it. There are actual multiple layers of attention in there, but it's essentially determine which tokens to pay more attention to in group. And so essentially how that works is you have query value. So maybe it would say, so within this example, we had John wants his bank to cash the. So the query could look first at his. And it would know, okay, well, it's looking for a noun describing a male person. And then the key would be John, a noun describing a male person. So it would see this and it has a match. This is actually done with the dot product, but we're not going to get into that. But once it sees that match, it can actually, because these are vectors, it can join that information together. And that is then gives it the attention when it moves along. So now his and John would move along and more attention would be applied to them because now John has his connected to it. It's just to kind of give you a sense, GPT-3 has 96 layers with 96 attention heads. So every time it's predicting a new word, it's performing an attention operation over 9,000 times. So that's a bit of a crash course through AI/ML. I also want to talk about a little bit about a foundation model workshop. So this was a workshop between SETI and NASA Ames back in February that I led. You can actually you can go to the QR, if you follow the QR code, you can go to the website for it. And the main point of this was to determine if foundation models would be a good fit for astrobiology. And if so, what would the possible use cases be? And what would be the next steps to developing a model or models? So now you may be asking yourself, well, what is a foundation model? And we've been talking about machine learning systems here. So a foundation model is just a machine learning system. It's just like a large language model. It's trained on enormous data sets. It understands the general information relationships amongst the data. And this serves as a foundation for downstream applications and tasks. Here's a visual. You have your data on the left, your pre-trained foundation model, and then your downstream applications. And GPT is actually a foundation model. That the large language model part is the foundation, and then chat is the downstream task. And within the NASA ecosystem, we also have the pretty harmonized Landsat and Sentinel-2 FM. This is a geospatial foundation model using HLS satellite data. It has applications from land use tracking, crop yield predictions. And I don't have it up here, but Goddard also has a internal chat that they've been developing, and you can get access to it through NAMS. So the workshop itself, this was funded by a grant through the Topical Workshop Symposiums and Conferences, or TWISC, and it consists of a virtual primer and an in-person component. So the primer was really because we had so many different participants coming across different disciplines. We wanted to make sure when we actually got together, we could all have a fairly similar knowledge base to discuss from. And so you can actually see the recordings from the presentations at the QR code there. And it was everything from astrobiology to data science. So a lot of what the ML that I was talking about today, we also covered that. And then the in-person was 3 days at the SETI Institute here in Mountain View, back in, I said, in February. And it started with presentations from the Astrobiology Research Coordination Networks. And essentially, they gave us a sense of their strategies and goals, and we had a back and forth with them to better understand that. And then daily breakout groups. We essentially started with a big laundry list of wants or desires for astrobiology, and then broke down into groups to essentially determine from those what may be plausible and kind of shake it all out and we shook it all out into these different bins of detection of life, missions, and AB chat or astrobiology chat. So the detection of life was this idea for a multimodal abiotic and biotic database with the specific purpose of biosignature detection as the downstream task. For the mission focused decision making, this was for a tool called the Astrobiology Mission Model, or the AMM. And the whole idea is you would use this both during the mission design phase, but even during mission operations. So you could imagine an onboard AI for a mission going out to outer regions of the solar system, maybe Europa, or Titan, and where you're going to have less energy available to you. And also you have less energy and you have more distance now. So it's going to be a lot harder to communicate. It's already very hard to have any kind of back and forth with the Mars rovers. There's a lot of coordination involved. So that difficulty becomes even more pronounced when you increase the distances to the outer region of the solar system. So having an onboard AI that could actually facilitate some in situ analysis and operations would be key. And then all of this would be interfaced through an astrobiology chat or the AB chat. This is just ideas in LLM. It would probably be built up from a current large language model. And amongst allowing you to interact with the detection of life and mission parts, it would also facilitate research gaps or identifying research gaps and hypothesis generation. This is a visual of our multimodal foundation model idea. So you have your data there on the left. This is that corpus of data would be trained on. You have your model, and then your fine-tuned tasks or your downstream tasks with the ability to add future applications down the road. We've also had a fair bit of output so far. We've had 2 DARE submissions, both just for the general workshop itself and then on the data ecosystem. And we're finalizing our first paper now, which will be a white paper to the news and views section of the Astrobiology Journal. So it's going to be foundation models for astrobiology. And we're expecting to actually submit that this week. So this is, I know there's a lot here. This is a general roadmap for an FM that we've laid out. In the near term, we believe the AB chat development could essentially begin now. Because, like I said, that would be based on a large language model, which we don't have to reinvent. And then the next steps would be getting all the various data together, working on the detection of life model and the AMM development or the mission design, with the ultimate goal of having a functional agentic AI tool that we could use. And then as far as just what we would be looking for from NASA and the community, in general, better integration with open science. This was a big thing that came up during the workshop, where there's discussions about data and funding. Funding both for AI, ML, whether it's within the ROSES program, and also training astrobiologists on AI, ML. So big takeaway from the workshop was to conclude that FEMS would represent a great and timely opportunity for astrobiology. We hope the workshop work will guide those future efforts. And then, so this is just a summary of what I went through today. So like I said, this is a fairly crash course through unsupervised and supervised learning. We did evaluation and deep learning, LLMs, a little foundation models. And then if you are looking to kind of get started on this, scikit-learn and TensorFlow and tidy models are a great place to look at. Tidy models would be if you're working with R, scikit-learn would be Python, and I believe TensorFlow can work with Python too. I have to double check that. So thank you.